All right, hello everybody, and welcome to our session of the Open Source Analytic Community. This is a follow-on event from the OSACon conference that we held in November. We're doing regular presentations on subjects related to analytic software and open source. Today, it's my pleasure to introduce Sita Shed from Stellar Data, who'll be talking about how modern analytic engines unlock the full potential of Apache Superset. With that, Sita, welcome. It's such a pleasure to have you here today,
Thank you.
and take it away.
Thank you. Thank you so much for having me. Yeah, so everyone, welcome to this webinar, and thank you OSA Con, thank you Opportunity and Preset for inviting me. It's a great pleasure to talk to you guys. So my name is Sita Shen. I am a product manager at Stellar Data. So we're a data company. We build a an open source query engine and data warehouse Starrocks, right? We're the initial contributor and the maintainers of the Starrocks project, and I am also a Starrocks contributor. So today's talk's topic is on BI. It's very interesting. It's how modern engines unlock the full potential of Apache Superset, right? So first, we're gonna talk a little bit about what is Apache Superset. And then we're gonna talk about the pain points that we see, at least in the Star Wars community, right? Well, the users are using Apache Superset, their pain points and challenges. And then we'll dive into the requirements, for the underlying engine to use, Apache Superset. And then we're going to talk about the technologies, that enables kind of that interactive analytics, for your BI and your Apache Superset. And then stay to the end. I'll have a live demo, right, to show you guys. So first, so what is Apache Superset? Apache Superset, I think, started as a hackathon project at Airbnb, right, around like 2015, if I remember correctly. It is an open source modern data exploration and visualization platform, right? It enables interactive analytics, right? So you can go there and just click and drag and drop and, do everything, on the fly, right? And you can build your dashboard with literally like no code. So drag and drop, right? And it is a very lightweight and a thinner layer in your data infrastructure. It instead of like doing all of the computation and storing all the data by itself, it leverages what you already have, right? The power of your existing data infrastructure without another ingestion layer, without another ingestion layer that duplicates your data, right? Very expensive, right? And it is one of the biggest or the biggest open source BI community we have right now, right? Just crazy number of stars, and with I think 15,000 people in the Slack community, right? So a very vibrant and active community that Apache Superset has. Join their Slack if you haven't. And so we do have a lot of Apache Superset users in the Star Wars community, right? And we do see a lot of challenges that they face, when they're using Apache Superset, right? So first is running dashboards, right? So they're battling with slow and unpredictable performance, right? I think one of the bigger challenge for Apache Superset is that the the user that actually create the graphs, the dashboards, and looking at the dashboards, making those business decisions are not the same group of people that actually maintain the infrastructure, right? So the user is not going to really care about, how expensive a query actually is, how many terabytes of data it's actually scanning, how many tens of tables that, that query joins together, right? They want fast performance, and, that running dashboard is really a big challenge for them, right? And second is really complex architecture, right? Apache Superset by itself is very simple, but to achieve a lot of that performance, users are maintaining a completely separate data warehouse solution purely to serve, those interactive dashboards and queries, generated by Apache Superset, right? That really complicates their architecture. And also the access pre-computation pipelines, right? Apache Superset, a lot of it is to serve those like internal use cases. So many different use cases, many different tables, right? And a lot of the query engines today are not really built to handle those like big joins at scale. So they're stuck with building many denormalization pipelines, which can be extremely expensive to do by itself, right? And also it fixes your kind of your schema into a single view. So when you every time you do like a schema change, you have to like data backfill. And pre-computation pipeline, just too many of the pre-computation pipeline is definitely a challenge that we see a lot as well. So what are some of the requirements, right? Performance-wise, you want to have those slice and dice analytics, right? So basically, the ability to compute everything on the fly, right? On rather complex SQLs with joins and aggregations, right? Sometimes higher cardinality aggregations, right? And still has that consistent performance, right? And then all queries needs to be fast, regardless of complexity I just talked about before, right? Because the users are not really the infra people, right? They don't care about like how complex the query is or how many terabytes of the data is scanning, right? So here are the requirements. So let's just start by talking about like how do you actually accelerate Apache Superset queries, right? So first, your tricks, your data warehousing tricks, your still apply, because that's ultimately the thing that's supporting your dashboards, your dashboard refreshes, right? Things like partitioning, right? Partition your data and sort your data, based on how you're going to query them, right? It's going to really reduce the amount of data that's being scanned, right? Indexes as well, right? If you don't want to do like, you have a dashboard that does like a massive count distinct, maybe a bitmap index, it's going to help a ton, right? And the right type of data types, right? That makes a difference as well, right? Int and string, drawing sometimes like 3+ times of performance differences, right? And your pre-computations, right? Materialize views, know how to use them, right? And know when to use them, right? And that's, all of the tricks and, just traditional like data warehousing tricks, right? And also you have to know about like how a query is executed, right? Especially on your query engine. Like, does your query engine do data shuffling, right? Like basically how it works, it's very important, right? Also take advantage of the specialized features that your query engine or underlying data warehouse has, right? And the next part is more of, you have to like care your data and metadata, through compactions and regular like metadata maintenance, right? This is more for those that are directly serving your dashboards on your data lake where, or otherwise this for a data warehouse, this is mostly taken care of by the data warehouse itself, right? And if you have like too big of a data file, scanning those data can be those file too small of the data file and too many of the data files. Scanning them can be very expensive. And for metadata as well, right? If you have too big of a metadata file, not enough of them, we cannot really parallel read. And if you have too many of small metadata files, like reading those can be very expensive as well, right? And also you have to understand how Apache Superset works. It is a thin layer that doesn't really do compute, but it does have a lot of feature that helps you with your performance, right? For example, like caching, right? Virtual data sets. And also you have to know like how often the your dashboard actually refreshes, right? So like how expensive the whole thing is to set up your infrastructure, right? And I think the most important thing is actually not all of that. It's actually you have to start with something that's correct for your use case. So you have to absolutely use the right engine for your use case. Let's just imagine if you're if you have requirements for low latency dashboards, let's say sub-second refresh time, right? And you have Spark on top of like let's say a Hive table, right? To serve that dashboard, it's not gonna really do very well. You can engineer the hell out of it to get the last bit of performance, but Spark is just not built for those low latency workloads, right? And also, you want to pick something that's built for OLAP, as columnar store, and this is what we're going to talk about in the following slides. So we're going to start from, I think, the very bottom, right? probably a little too bottom for the audience today, right? Very basic stuff, right? So you want to choose an engine that is built to run analytical queries instead of, transactional workloads, right? So you have OLAP, online analytical processing, versus OLTP, right? So which is online transactional processing, right? They're built for very different purposes. So OLAP is more for like problem solving, decision support, right? Data discovery, supporting reports and dashboards. And OLTP are those, that are the core that runs the business operation, right? So for the queries, OLAPs are, multi-table, sometimes single table queries with mainly aggregated queries, right? And OLTP are those, simple standardized queries, select word, those point queries, right? And so record level data queries, right? And for data volumes, OLAP tends to store a lot more data, right? A lot more historical data, because you want to extract the insights out of them, right? So massive amount of data, from historical data and pre-aggregated data or pre-joined data, right? And for OLTP, it's mainly, you maintain that current real-time data that's typically compact and transactional in nature, right? And update frequency, OLAP, let's say with deletes and upserts, you're looking at something like sub 10 second is probably pretty good, really good for OLAP system, right? So it's mainly batch and near real time, right? And OLTP are very frequent, like record level, just 1,000 people, writing the same table at the same time, and even more are reading at the same time, right? And somehow they keep it working. That's pretty miracle. Yeah, and so this is data update frequency, and I think the easiest way to distinguish from something that's built for OLAP and something built for OLTP is how the storage is oriented, right? So OLAP is mainly columnar store, or a hybrid between columnar store and a role-based index, or columnar store with a row store, right? And OLTP systems are mainly role-oriented, and we're going to talk a little bit of that in the next slide. So to get efficient query execution, query processing for OLAP, right? OLAP typically use columnar storage. The reason is, just think about a typical like analytical or aggregated query, right? Just like something that's, like for all of the people that joined the webinar today, right? How many of them are wearing a pair of glasses, right? So you're basically scanning all of the data by column, right? And then do like an aggregation on that column. So if you calculate or process things by column, why not store them by column, right? So we use columnar storage, right? So it's oriented on the columnar way, right? And this is great for OLAP as well, because you get really good compression ratio, if you are, storing things by column, right? And also vectorization basically says we store by column, and when we process everything by column as well, right? So basically batch processing, for OLAP, it's just the more batch you run, the faster it goes, right? And everything is processed in batches. And this is a lot more CPU cache friendly, because everything you do is in a batch, right? It's ordered. And also it's very easy to, a lot easier to incorporate SIMD optimizations, when you're execute everything by batch, right? So, and SIMD plus vectorization plus columnar storage is probably the most important thing, you need to get that great performance for OLAP, right? And CMD basically means, one is for every single CPU instruction. Instead of like processing one data point, we process number of data points, right? 128 to 256 bits of data, right? And so here's an example, right? So on the left, this is how would you do without SIMD, right? It's two vectors, a scalar addition, right? So you have to, every time you add, right, you have to read them one by one, right? Either from memory or from your CPU cache, right? And this is very slow, right? But with SIMD, you're able to do read at the same time, add at the same time, and so it's a lot faster, a lot less touching on the memory, so a lot faster, right? And Starbucks has this optimization as well, right? We've done it, and we yield So just the vectorization and CMD alone, we yield around like 3 to 20 times performance gain, operator by operator, right? So that's why we have the AVX2 instruction sets, requirements for Stardogs on the CPU side, right? And this is super important if you are looking for just the best performance for your Apache Superset dashboards, right? Find something that's columnar store, has vectorization, and it's written in a lower level language so you can take advantage of CMD, right? So next is the computer architecture, right? So that's we talk about like how thing is computed, right? It's on a single node, and this is more like distributed, right? So you have different kind of computer architecture that are optimized for very different kind of workloads, right? First, you have that more traditional like scatter gather, right? So you have a bigger node, that distribute all of the sub jobs to the other nodes and back and reduce to that one node and do some kind of like final aggregation or processing, right? For this kind of architecture, once the data is assigned to a node, right? Let's say a tablet or a shard is assigned to a node. It cannot really reshuffle during the query process, right? So let's think about like for a join, right? You can do a broadcast join, or you can do a co-located join or a local join, right? But you cannot really do a shuffle join. It doesn't shuffle data like during the query processing time, right? This is a very robust and simple architecture, really great for those use cases that has simpler queries, not that many joins, not that many high cardinality aggregations, right? But you want really high concurrency, right? This is a great architecture for that. But for those like more complex queries, it's easily bottlenecks on a single node, right? And then there are those like more batch approaches like MapReduce and the stage by stage. That's something like Spark does that evolved from MapReduce, right? It does have a data shuffling service, a shuffling process, but is completely based on disk, right? So every intermediate result is persisted disk, right? So there are wait time before tasks. Not that it is trying to slow down query on purpose. It does that for stability reasons, right? Have a Spark job, I can trust it to run for a few days, without any problem, right? If it breaks, you can actually restart from the middle, that. So it's great for batch processing, but not really for like low latency, those high concurrency workloads, right? And then there is the MPP, right? So also shuffle data, but instead of like using disk as the intermediate, like to store the intermediate results, it actually shuffles between the nodes of the memory. Oh, sorry, the memory of the nodes, right? So it actually it streamlines the process, So there's no like absolutely zero wait time um between tasks, and in-memory data shuffling and also ensures you have that scalability because you're able to distribute the data while the query is processing, right? So you can do a shuffle join, like two big table joins, and also you can do something like if you have very high cardinality aggregation, you can do multi-phase aggregation, right? You can do a local one and then do a shuffle and then do a second phase, right? So this is great for those like sub-second joins and with high cardinality aggregations at scale, right? So for big data, this is very good, and also you get that lower latency without touching disk. Right. So this is the kind of like the computer architecture, what you want to pick based on your own use case. Right. So next is we talk about execution, we talk about distributed compute, and then is the query processing. The query planning. I'm sorry. Right. So query planning is it's a very difficult and important problem to solve, right? So it's like going from point A to point B, right? If you take the wrong route, it doesn't really matter how fast you go. You're not gonna get there really in time, right? The search space to execute a query is just stupid. It's just stupidly big. It's enormous, right? You think about how you order your join, right? Which join algorithm to pick, right? Do you do a nested loop join, or that's how on the single node, how is it executed, right? And also you pick, which kind of distributed join strategy, right? Let's talk about something like a broadcast join versus a shuffle join, right? And also aggregation methods. Also, and optimizers can do something like a runtime filtering, right? If you have two tables that join together, actually can use the filter of one table and funnel that into the other table, so you don't scan as much data. So, an optimizer can do so much, to make your query run fast, right? To make join actually work, for OLAP, right? So now the state of the art approach is a cost-based optimizer. So what it does is that it collects real-time statistics from your data, right? So it's using the statistics of your data to compute the cost of every single candidate plan and basically pick the cheapest one that's in there, right? So, and the cost-based optimizer needs to be natively built and is deeply integrated with, the execution and storage layer, right? And and we built that, and it was impossible to get it right in the first try. So, luckily we're open source, and we could iterate with the community, right? It took us like a year, 2 years to get it right, right? So this is cost-based optimization, and okay, so this is, basically how the higher the bird eye view of how you get, great performance for your kind of like overlap workloads for your Apache Superset dashboards, right? But the next question to ask is, those are all like data warehouse features, right? Or people usually run them on data warehouses. So do we actually need a proprietary data warehouse to achieve all of the things that we've talked about, right? So here I'm going to talk about actually the challenges that comes with, having a proprietary data warehouse, a challenge that comes with moving your workload into a proprietary data warehouse, right? Your workload and your data, right? So first you have to consider the cost of actually maintaining that data warehouse itself, right? So it's stateful, it stores a lot of data, use a lot of resources, error prone, right? It's very expensive to maintain, and by itself, it's very expensive as well, right? And also you have to consider the cost of actually the data ingestion pipeline, right? Writing your data from one format to another, doing that for terabytes, petabytes of data. That's a very expensive process, right? Not only that, you have, ingestion pipeline for each table, thousands of tables. Just think about that. Very nothing thing to do, right? And also you have to consider the challenge of actually, matching the schema, right? Data ties between your data warehouse and your data source, typically a data lake. We see a lot in the community, right? And also, most importantly, I think data governance is the biggest challenge, from doing this, right? So you're basically duplicating your data from your data lake to your data warehouse. So you're breaking, the single source of truth, right? Of having a data lake, right? So now you have two copies of data that you have to manage. You have to keep sync. You have to keep the quality high, right? And that's a huge challenge, right? So why are people actually moving their workloads and their data to data proprietary data warehouse, right? All of those features, actually, a lot of them are starting to be available, on the lakehouse, right? You have those iceberg tables, you have those like hoodie delta tables, they behave just like a data warehouse storage, right? It's because the query engines that are used for data lakehouses today are not really built for data warehouse like workloads, right? Some of them are optimized for long running batch workloads, not really low latency, high concurrency queries, right? Or some of them are not even optimizable for performance, right? They're written in a higher level language um, to make to build connectors really fast, great connectors really fast. They're optimized for many data sources, but not optimized for a few, right? Those lakehouse or open table formats, like those iceberg and hoodie tables, right? And also on the technical side, I think one thing that's the biggest difference between a data lake query and a data warehouse query is, fetching data, metadata, the cost of doing that, right? So first you have to like consider the network IO, right? You're moving data, from your data lake, probably sitting on S3, right? You're moving that during query time, right? Query execution time, and that takes a lot of resources and very slow, right? And also you have to consider the slow and unpredictable performance of uh, your data lake, just basically the your storage device, right? S3, let's say for AWS S3, the latency can be upward to 100 milliseconds, which is just a little too slow for those low latency query scanning, right? Data scanning. And also data files can be unoptimized for query performance, right? Maybe just talk about like too many data files, metadata files, too big, too small. It has to be the right size and amount, for it to have the best possible performance, right? So how to accelerate data lake query performance, how to get that data warehouse like performance, on a data lake house. I'll touch on a few points and I'll show some data points later on the slides, right? So first, a hierarchical caching formula is absolutely necessary for your metadata and your data files, right? So first, to overcome the unstable performance of data lakes and also to save the I/O cost of actually fetching the data from your external storage, right? And also you want to pick something that's absolutely optimized for low latency instead of those ETL kind of pre-computation kind of workloads, right? You want to pick something that's MPP. It does between memory data shuffling, right? And also you want to find something that's actually optimizable performance. So you want to find something that's built in lower level language like C++, right? To fully utilize your SIMD instruction sets, to fully realize the power of vectorization, right? With the right tools, getting data warehouse like performance on the data lake or data lake house is actually quite easy to do, right? I'll show you some data points later. So here I want to introduce Starox. So the reason why we use Starox here is because we want to compare data warehouse and data lake performance, right? And Starox actually has two deployments methods. So first, it has its own optimized storage engine, right? You can do real-time data upserts with, and it has probably the best performance, one of the best performance in the industry right now. Absolutely the best for join, but for aggregation, one of the best, right? So that's your own storage engine, right? And also you can basically ditch the SAR storage engine and connect your data lake directly to it, right? So basically you can use Staros to directly query your Parquet files managed by, let's say, an iceberg table, right? Directly query that and still get great performance. And I'll show you how those optimizations just talking about help Staros does exactly that, right? So first, let's set some baselines, right? Staros is extremely fast as a data warehouse by itself, right? So this is a SSB benchmark test comparison between Staros and Apache Druid, right? So Staros 3.0 versus Druid 25.0.0, right? So SSB 100 gigabytes. So to be in mind, this is the flat version of the SSB. So only the on-the-fly aggregations are run, not the on-the-fly joins, right? So no join, only aggregation. And Staros is around like 8.7 times faster than Apache Druid, on this flat uh, flat SSB benchmark test. This is mainly coming from the vectorization and SIMD, right? Written in a different language. And also there's one part I didn't include in. So actually we did a test on the Starox 3.0, for the original SSB test with the join. Actually with the join, still faster than Apache Druid's single table performance. So you basically get that join, for free. Right? So this is just to set a baseline. So Staros as a data warehouse is extremely fast, right? So now let's do the comparison, right? So Staros as a data warehouse versus Staros as a lakehouse query engine, right? So this is a little more complex data set. So it's a TPCDS 1 terabyte benchmark test. So this is more complex queries. So you think about something that your data scientist would write, right? So those ad hoc queries with a lot of joins and aggregations on just very high cardinality columns and multiple columns, right? Hot queries, same exact hardware. The data warehouse solution is only like 12% faster. So with the right optimizations, you can gain all of the benefits of having a lakehouse, having a single source of truth data, right? Having not to move your data and having not to have a proprietary data warehouse that you have to maintain, right? Just 12% the performance penalty. I think that's pretty good, right? So yeah, so this is another comparison, Staros purposely built for data warehouse like workloads when compared to Trino, right? Trino was built to connect to many data sources and get good performance, right? So Staros is around like 4.6 times faster than Trino on the same benchmark test we just talked about before, right? And this is even with Trino on JDK 21, so that's supposed to have that auto SIMD thing with Java with the new JDK update, but still we still have a pretty healthy lead on there. Yeah, so this is what you get, for like having the right, kind of optimizations, right? So this is just for this specific workload. Okay, so we talk about raw query performance, and that's definitely very important for your dashboards, right? But it goes way beyond just fast queries, fast raw query performance, right? Like you mentioned before, right? For your dashboards, you don't know what your user is gonna connect the dashboard to, right? They don't care about like how big the data is or how complex the query is, right? Sometimes you still need pre-computation to accelerate, those slow queries, right? So let's imagine you're a data engineer, right? And you identify some slow query, right? And you figure out that the only way to fix that slow query is to add a pre-computation to a pipeline, right? And let's say you use Spark to do that, right? You created let's say a denormalized table between a flat table, just a denormalization between the three tables, and that solved the performance issue, right? But it's not going to really take effect until your user or one of you, rewrite the SQLs to point to the new table, right? For Apache Superset for BI, basically to reconfigure the dashboards, to be able to take advantage of that performance boost, right? And this is such a painful process that actually forces engineers to figure out, all of the data pipelines prior to developing their client-side application, aka the SQL scripts or the dashboards, right? So when they plan a little more than they need, right? So they end up building pipelines that generate tables that really get used or never get used, right? And this whole planning process, it's just so much testing. It extremely lengthen your development cycle, so you end up going to production way slower, right? I think the reason why this happens is because people do this when query engines are running slow, right? Just think about like 5, 10 years ago. We weren't even doing aggregations on the fly, right? So everything was pre-computed, and you pre-compute everything with a Spark cluster, and sometimes you store that in a MySQL database to serve your analytical workloads, right? And now query engines are running so much faster now, right? So you actually have the option to only pre-compute on demand, right? So your user has the flexibility of actually doing drill down and slice and dicing, right? Doing those queries on the fly, right? So I think this is where the mismatch is coming here, right? And the solution, that we came up with on the Staros side is materialized view, right? Materialized view has been a feature that's been around for like decades, right? And so it's basically a table, right? So you pre-compute into a table, right? So Staros materialized view is just like a materialized view. It can it does that it does basically you can use it for pre-computation, right? You can do denormalization, you can do pre-aggregation. It works with multiple tables, and automatically keeps your materialized view and your base table in sync, so you can keep your single source of truth still, right? Even you have materialized view on top, right? But the biggest thing that the Staros materialized view can do is its full query reliability, right? So basically, when you do create a materialized view, Staros cost-based optimizer for a new query that comes in, Staros cost-based optimizer can actually automatically route that new query to the most appropriate materialized view, right? So you don't have to change the SQL, right? So it's ultimately a way better user experience for your data user, right? Because you take advantage of that pre-computation immediately, right? Without actually, modifying your SQL, right? And this enable you to add, your query acceleration or pre-computation on demand after everything's already built, right? You fix those slow queries on demand, right? And it ultimately save compute and storage from, those unnecessary pre-computation pipelines that we just talked about before, right? And ultimately you can go production way faster, right? And the query rewrite capability supports all SPJG queries, right? So say select, projection, joins, and group by, right? So it does have some limitations, right? But we do have ways to bypass that limitation. I'll talk about a little more about this during the demo, right? So how to bypass SPJG rewrite limitation, we do have a view-based rewrite. So if you encapsulate your query logics into views, and then you turn it into materialized views, it's going to work automatically, right? Without the SPJG rewrite limitation, right? You can have window functions in there, and it's still gonna work, right? So this is just a few of the optimizations we did for materialized views, right? Just to get, the best possible user experience for you guys, right? And we also have many more, detailed targeted optimizations to ensure the absolute, best user experience, to get the most out of materialized view, right? Let's see this. This is a join on top of aggregation query, right? And and materialized, you can actually rewrite this and use a materialized view to accelerate, the aggregation, right? So basically push down the aggregation so you don't so the joint doesn't run as much as the joint doesn't run on as much of the data, right? So yeah, so this is a materialized view, and all of this together is supposed to give you really good Apache Superset experience, to enable you to actually have that interactive analytics, with everything being computed on the fly, or most things being computed on the fly, right? So here I'm gonna do a demo. So first I'll basically talk through what the demo is about, right? So we're gonna have preset as a BI layer, right? Preset is basically a cloud service that's powered by Apache Superset, right? And we have cellular data as the compute. We use cellular data cloud BYOC, and this is powered by Starrocks, the cloud version of Starrocks, right? And we have AWS Glue as the metastore, and Apache Hive as a table that manages Parquet files that sits on top of AWS S3, right? And for the data set, we have two. Because we're just directly querying on Lake, we're not really doing any ingestion, so why not, having more data sets? So the first one is gonna be on TPCH 100 gigabytes. So for this one, we're gonna use the TPCH query number 5, right? Because it's simple looking and it's very expensive. We're gonna demonstrate just how query rewrite can accelerate your dashboards without actually changing the dashboard itself, right? And then we're gonna do another showcase of the view-based rewrite. We're gonna use the SSB 1 terabyte dataset, right? Just came up with a stupidly expensive query and see how view-based rewrite can help us accelerate that, right? And let's go into the demo. Let me share my screen. Just 1 second. Okay, you guys should be able to see my screen. And now we're in the, move this away. Now we're in the Cellular Data Cloud BYOC console. And yeah, so this is basically the cloud version of Starrocks, right? The cloud commercial version of Starrocks, right? So this has a BYOC kind of architecture. Basically means that this whole thing is, so the Starrocks itself, right, is deployed in your AWS account, in your VPC, right? And we have that manager service that in our VPC that help you do the maintenance, right? Basically, you have ownership of your entire data infrastructure while having the benefit of having a cloud service, right? So here is that, and okay, so and we already connected seller data through the Staros connector to preset, right? So we have two here. So one is the glue catalog, and this is basically the catalog that connects to AWS Glue, the data lake, right? And we also have an internal catalog here. The reason why is that we want to do the view-based rewrite, and the views are stored in the internal catalog, Staros managed catalog, self-managed catalog, right? So that's the connection here. And we do have the right to. So these two queries I want to demonstrate. So one is the TPC-H number 5, and this is one I created just for the view-based rewrite on the SSB 1 terabyte benchmark test, right? So how we're going to demonstrate is that, so here is a global parameter that we tune, right? So enable materialized view rewrite, true or false, right? So this normally would be true. Who modified me? Okay, never mind. True, right? Okay, so this normally would be true, right? And so this is the kind of like the default setting. And so this controls whether Starock CBO actually rewrites the query, reroute the query to the materialized view or not, right? So this is default behavior. And now we just flip that to false for now. And let's just run this query for now because it's going to take a very long time. Yeah. And let's look at query number 5 for now. So this is a query that's being run here. This is a pretty expensive query, a simple looking, but pretty expensive. So this is a join between 6 tables. With line item, the biggest table in TPCH, I think for 100 gigabytes, that's 600 mil rows, I think. And then the group by here, right? So this is a pretty expensive query, even for Starox for seller data. Now we see the result is complete, and let's take a look at the query history and find that query. It ran for under 8 seconds cold, so that's already pretty good, right? Because it's 6 tables after all. So let's take a look at the query profile. So yeah, see a lot of joins. And after that, we do that aggregation on the name column, I think. Yep. So yeah, it took around 8 seconds on 4x large, 3 of that. That's 48 cores, right? Okay. So what we're gonna do now is, without actually changing anything here, right? We're just gonna flip this to true because we already created a materialized view here for this. Okay, here is a materialized view, right? We already created a materialized view here to accelerate that query. So this materialized view looks pretty scary, but it's just mainly just foreign key constraints because we're creating materialized view directly for a data lake table, right? So you have to add those foreign key constraints. It's pretty standard, but it is just a denormalization between all of the TPCH tables, every single TPCH tables, right? You can see the materialized view here. So it's 600 million rows here, right? That's already created. And we just flip this thing to true and see what happens. Okay, that was done. That was pretty fast, right? Let's see if it shows up on the history already. It does take a few seconds to show up here. Okay, so here we can see that this is the exact same query that got sent, generated by Apache Superset, preset powered by Apache Superset. Exact same query, but the query profile, instead of having all of those nasty looking joins, so this is the old query profile. Instead of having all of those joins and scan directly on HDFS, so on your data lake, so what it did was it just read from the materialized view we just showed, right? So the denormalized version of TPCH we just created, right? And then did an aggregation. and the whole thing was run in under 150 milliseconds, right? So without changing anything on the dashboard side, right? So this is the first thing I want to show, just a vanilla version of how query rewrite works when your query is SPJG compliant, right? So only has select, projection, join, and group by, right? And here I want to show another one, right? So basically the view rewrite version of the materialized view. So this is a lot more flexible, right? So let's first flip this to false. So we don't want it to rewrite. Let's refresh this because it's gonna take way longer. This is a very expensive query that I made. So okay, so basically what I did was I wrote a query, right? That has a window function here. So this is very expensive without, I don't think I even included a predicate here. Yeah, so this is on the SSB 1 terabyte benchmark test, right? Storing as Parquet files on a Hive table, right? On AWS S3, right? So I created a view, and in preset, I just get it to query this seller data view directly, right? And okay, it's finished. Let's take a look at the query. 26 seconds. Wow. Okay. So here's the query profile, right? So you see it did a join. It directly scanned from the Hive table. It did a join and did that aggregation, right? Okay. So what we're gonna do here is that so we've already turned this materialized turn this view into a materialized view, right? So because this is not really rewritable without a view rewrite, right? So we basically turn this view into a materialized view, right? And let's see the configurations. We just flip that to wait. Who's changing my? Okay, we just flip this back to true, and we do that again. Okay, that's done. So basically, it barely did any calculation. It's because it directly scanned from the materialized view, just created from the view, right? Let's take a look. Give it a few more seconds. Oh, here it goes. Okay, from MV view rewrite. Okay, that's the same query. Okay, so it directly scanned from the materialized view. That's why it was able to run that fast. Let's take a look at this one. So this is the one that ran for 26 seconds before, exact same query, and the query profile looks like this. And actually, Stellar Data Cloud just released a new feature. We just had a webinar that released a new feature that talked about automatic materialized view, right? So now, if you're a Stellar Data Cloud PLC user, you can actually get those materialized views automatically recommended to you, right? So you don't have to think about like how to do partitioning and how to create a view materialized view that's generated general enough, for many of your queries, not just one, right? So you can, so you're also welcome to check that out. And this is all for my demo. Let's go back to the slides. Okay, this is actually all I have. So you can try Stellar Data Cloud PLC today and get your 30-day free trial at cloud.stellardata.com, right? So you can try materialized view actually with automatic materialized view, right? And then join the Star Slack community here. You can also scan this code to join, right? So do we have any questions?
We do. So I've got one
Let
from
me
email.
see.
A How does Starrocks compare to ClickUs? I'm sure you aren't surprised by that one.
Wait, where are the questions? How does Starhouse compare to ClickHouse? Okay, so let me figure out. Yeah, so I think those are Starling and ClickHouse are excel at very different things, right? In my experience, ClickHouse was, correct me if I'm wrong, sorry. So was created for those like log analysis, right? ClickHouse has absolutely great aggregation performance and great compression, right, for ClickHouse. And StarRox, I think when you want to consider StarRox is two things. If you have way too many tables, and you absolutely cannot afford to denormalize, right? You have many tables, and then you have really big data set that just doesn't fit uh, into one node. So uh, two big table joins, and you cannot afford to denormalize. This is when you would consider Staros because Staros is built, to run those big joins on the fly. And also another use case is, the upstairs deletes. Staros does have a special feature that the primary key table that allows you to do upserts and deletes without impacting performance and still have around like sub 10-second data freshness, right? So those two are, kind of like the use cases that you might, consider using Starrocks instead of ClickHouse, right? Both of them are fantastic projects. It just depend on like what use case you have or and the requirements.
Great. Yeah, that was a wonderful question and a very generous answer. I had a couple of questions. The first one is which are in the chat. The first one is you talked about data lakes, and that's a very interesting capability. But I wondered, update and delete are very hard
Yeah.
in data lakes, and I'm just wondering how Starrocks handles those operations, or do you have to design around it, use Spark or something else to make changes, say in Iceberg? If you could tell us a little bit
Yeah,
about that.
yeah. So I think yeah, for data lakes, updates are challenging now, but it's a lot less challenging now when compared to like just a year ago, right? You have new projects like Pyman that's coming out with that, primary key record level index. You have Hoodie and you have Delta, right? And those Delta features, I just had a webinar with one of the Databricks PMs at our Celidata webinars, and they're talking about actually migrating those Delta features into Iceberg, to
Hmm.
have to support those like higher or not higher, better data freshness, right? For your open data lake tables, right? And for now, how we handle it is like for our users, if they actually want like 5 second data freshness and they have the leads and they want fast performance, they basically ingest into Starrocks. And that's the thing for now, right? To take advantage of our kind of storage engine for those like really fresh data and use data lake for the rest of the not that fresh data, right? But I think the lakehouse field is evolving really fast,
Yeah.
and we're going to see a lot of innovation in the very near future.
Yeah, that's
And we
right.
already do.
And Starbucks, you had your picture, this great picture of showing sort of the Starbucks native storage organization versus the uh, data lakehouse organization. And are can Starbucks do tiered storage? For example, can you have a table that where some fraction of it is stored in the Starbucks native format, and then the rest of it in a data lake? Is that possible today?
We in the data lake or in S3?
This is actually specifically in a data lake.
Oh, in the specific in the data lake.
Are you able to
So
do tiering across those table types?
uh no, because they though that would be like that's like two table formats, right?
Yep. Yep.
But
Exactly.
we do have a user that use it that way. Uh
Yeah.
yeah, Tencent Games, they basically use Staros as like the, how do I say it? The uh intermediate layer, so the
Hmm.
real-time ingestion layer,
Yep.
and they utilize Starrock's sync to Iceberg capability to sync to Iceberg every 1 hour.
Right. Yeah.
So like a cache for data ingestion, right?
Yep.
And they're able to get like sub 10 seconds data freshness with a single source of truth data on Apache Iceberg.
Right.
We do have users that use like that. And for the capability itself, there's a lot of infrastructure that has to build around it. But we're definitely thinking about it.
Great.
So as a
And
solution.
and then a similar question, sort of related question, inserts into data lake, particularly concurrent inserts, are really, again, pretty tricky because Iceberg effectively has table locks in their
Yeah.
formats. So is the best practice to just do a bunch of different tables and union them, or how do your users build systems that handle that kind of thing in data lakes?
Yeah, this is this is definitely a complaint that I've heard before. Um, so yeah, it really depends on the use case. I mean, I can't really say for sure, what is the
Yeah,
best approach to this, but I'm sure the Iceberg community is working on this.
right. Yeah, I think so. What is your? I mean, you made an interesting point that you felt that that there is going to be some merging of the technologies here. Sort of Delta features coming into Iceberg. What's your take on how this market is going to evolve? Do you think people will eventually, that the storage will evolve to the point where you can do real-time systems fully on data lake data, or do you think there's always going to be a place for the kind of proprietary storage formats that most of our products have today and that they use for real-time response?
I think, thank you. Great question. I think in the near future, a proprietary format definitely has its place, right? But
Yeah,
I think what the market and what the users are asking for is pretty clear by now. Is they want open formats, right? And they want basically open format for them is ownership of their own data, right?
right.
And I think with this technology keep evolving for a few years, we're definitely gonna see more space, more workloads that are being able to run on open formats, right? And this is my take. And also, I think table formats are not gonna be. We have that word right now, right? But uh, different table formats are actually, I think they're they're different. They're not compatible now, but they're
Hmm.
solving similar problems, right? And we do have projects like Xtable
Hmm.
from the hoodie from one house, right? And we do have Uniform from Delta, right? That also
Yeah.
try to tackle this problem. So we don't, do that false choice thing, right? So I
Hmm.
think, Lakehouse now might look uh, immature or
Yep.
there's actually more work you have to do. But in the future, I think it's gonna get a lot simpler and it's going to be able to support so many more use cases.
Absolutely. I mean, it feels like kind of where Kubernetes was a
Yeah,
few years back, where Kubernetes couldn't
yeah,
handle data, and then it started to get better and better.
yeah,
It's a really exciting field.
yeah.
We're at the top of the hour, out of
Do that.
questions. Thank you very
Thank you.
much. And for
Appreciate that.
everybody else, have a great day and thanks for attending. Talk to you soon.
Thank you. Appreciate
Bye.
that. Thank you.